Hello, everybody. Welcome to Sensation and Perception, Part 1. So we've been talking about brains, we've been talking about neurons and parts of things, but now we need to talk about the processing of that information because there's a difference between sensing something and perceiving something. Sensation happens in your sensory organs, like your eyeballs, your nose, your tongue, your fingers, right? Those sense things. But then they get sent to your brain, the signals, the information gets sent to your brain where you perceive what is really going on. So when you actually see something, when you say, "Oh, I see a dog," what you're doing is you're actually perceiving a dog. Now, first, the sensation comes through your eyeballs, right, where the light reflects off of your eyes, and that is sensed in your eyeballs. But when you actually put together all of those sensory impulses into something meaningful and identify it as a dog, that is a perception. Perception happens in the brain, sensation happens in the sensory organs. So when you hear something and you're like, "Oh, that sounds great," well, the actual music, right, the understanding of it as music is your perception. Sensation is just the sound waves coming in and being picked up by your ear, right, by your inner ear. We're going to talk about that later on. So sensation and perception. So for you, in order to see something, you got to be able to sense it, and then you have to be able to perceive it as well. It turns out that what you perceive is not actually accurate. I don't know if accurate is the right way to say it. I mean, it's not consistent. It's not the same as what necessarily is uh, being sensed or what the light is reflecting on. Is what I'm trying to say. What do I mean by that? Well, we'll show you that in just a little bit. But first, let's talk about how we're going to talk about some optical illusions. By optical illusions, we're really going to talk about ideas of perceptual illusions, because most optical illusions don't actually happen in your eyes, they happen in your brain. We'll talk about several different ways why this might happen. All right, so let's start with this. Let's say that, let's make a distinction between sensation and perception based off of this particular picture. Let's say that you're walking your dog in the park. Okay, what's actually being transmitted to your eyeball and then to your brain is not this picture, it is this. Your eyeball, flips the image of whatever you're looking at. So the actual light that is reflected on the back of your eyeball, that's called the retina, right, is upside down. So, for example, these are called inversion glasses. You can make them or buy them, right? What they do is they actually make the entire world look flipped upside down. So you can walk around and everything looks upside down. What's ironic about that is that your eyeball is already taking all the information and flipping it upside down when it goes through your lens, the lens of your eye. But then that upside down image is sent to your brain. And your brain says, I don't like upside down. I don't like it. I'm going to flip it right side up again. What you sense in your eyeball is upside down. What you perceive is right side up. Now, what's interesting about this is that there was a famous case of a researcher who decided to wear these kind of goggles for not just for a few hours but for a few days. And it turned out that over time, his brain got sick of it and flipped things right side up. So after a few days of wearing inversion goggles, he started perceiving things as right side up again. Even though his eyeball was looking at what the actual reflection of what was putting onto his eyeball was right side up, and therefore his brain normally flips it upside down. His brain got sick of it and reinverted it. He started to perceive what you normally perceive, right? Which is right side up. Sensation happens in your eyeball, perception happens in your brain, and sometimes your brain is not actually perceiving what it's literally sensing. Let's do another example. Microsaccades. Micro means small, saccades means jumps. So your eye is constantly twitching. So when I'm doing this, it's as if I had a ball right here, which was your eyeball, right? And these fingers around it, these are the extraocular muscles. Extra means outside, ocular, eye. These are the muscles outside of your eye, the things that move it around. Well, what happens is your eyeball is constantly twitching. And this, it takes in a lot of information, right? It helps you to take in information all around. Does anybody, do you right now, do you perceive twitching? As you're looking at your screen, is your screen twitching around? If it is, it's probably a problem with your screen and not with your eyes. But your eye is sensing twitches, right? So what is actually being sent to your brain is twitches. But your brain says, I don't like twitches. I'm going to keep it stable. Microsaccades, small jumps. What's really interesting, though, is if you get into a pitch black room, I'm talking pitch black, right? You get like a laser pointer. And you shine the laser pointer, like put it on a table, and so it's stable, shine it against the wall, okay? So there's only one point of light in the entire room. That's the only thing you see, is that one point of light on the wall. What will happen is your brain will say, gosh, normally I'm twitching around like this, and I'm picking up contextual cues so that I can actually fill in the blanks and make sure I have all the visual field. I don't have those anymore, so that thing must actually be twitching around. It's called the autokinetic effect, right? Auto, self, kinetic movement, the self-movement, autokinetic effect. A point of light in a pitch black room, if you stare at it long enough, it will start to move around, even though it's not really moving. Why? Because you start to perceive the twitches, the microsaccades that your eye is actually doing. I want you to look at this. This is not a video. This is a still image. Now, I know that some of you don't believe me on this, but I promise it is a still image. If you look at one of the dots in the middle and then move to another one, in your peripheral vision, you should see movement, right? Now you'll notice that this only works when you're moving between things. Some people believe that this might be caused by those microsaccades. If you want to, you can find this image on the internet, you can print it off, and you'll see the same thing. Those things are not actually moving. You are not sensing movement. You are perceiving movement. The perception happens in your brain. Your brain says, based off the context of everything I know, those things should be moving around. All right. Quick quiz then. When light passes through the lens and onto the retina, the image is rotated 180 degrees. 180 degrees. It's upside down, right? So your lens actually rotates 180 degrees, and then your brain says, I don't want it upside down, and inverts it right side up again. Okay, let's do another example. We're going to talk about a blind spot, and you can do this with me if you want to. So here's how this is going to work. I've got a piece of paper. All right, can you see my piece of paper? I don't think you can. If I get it close to me. Pick the non-white piece of paper so that we'll be able to see it. That's too bad. You're gonna have to just trust me that I have a piece of paper in my hand. That's really too bad. Huh. All right, well, I have a piece of paper in my hand, and here's what I'm gonna do. I'm gonna draw on that piece of paper a smiley face, and then a few inches away on the same piece of paper, I'm gonna draw a heart. So it doesn't have to be very big. I'm drawing a smiley face, and then I'm about 4 inches away, I'm drawing a heart on the same piece of paper. Okay, this is my piece of paper. It's too bad you can't see it with the keyer, right? But on here, can you see my pen? Maybe you can see my pen, right? So about the distance of a pen length away, I have made a small happy face and a small heart. Okay, that's what I've done. So here's what I'm going to do. I'm going to hold the piece of paper at arm's length, right? Arm's length away. Okay, then I'm going to cover my left eye. You have to cover your eye or else this doesn't work. And I'm going to focus on the happy face. I'm going to stare with my right eye at the happy face. And then I'm going to bring this forward until in my peripheral vision, I'm still looking at the happy face, but in my peripheral vision, the heart has disappeared. It is gone. It's not there anymore. And then I move it, I can see it again. Okay, so You start with it arm's length away, you move slowly forward, and boom. Right there, I can't see the heart anymore. This is because you have a blind spot in your eyeball. Now, how many of you are you perceiving a blind spot right now? Do you perceive a dark space in both eyeballs? Right? No, you don't. You don't do it. What happens though is you have a blind spot. You do. But you don't perceive it because your brain takes the information around it and fills it in. Now, what was going on there? Let me show you with this. All right. So let's go through the parts of the eyeball and make sure that we know what parts are which, just to make sure that we are all okay. So have you heard about the cornea before, right? So we're talking about people having cataracts and things. You're talking about the cornea of your eyeball. That is A. So A is the cornea. Whoops, that's not supposed to be a line right there. Let me get rid of it. Okay. A is the cornea. B is your iris, right? So that's the colored part of your eyeball. C is the lens. The purpose of the lens is to focus light onto the back of your eyeball, which we'll talk about in just a second. Okay, that's the purpose of that lens. It also inverts it. It flips it upside down. Okay. D is your pupil, the black spot in the middle of your eyeball, okay, where the light goes in. E is the aqueous humor. It's really just kind of like this watery thing that makes a space between those. It just is, it's kind of there for structure. F is the ciliary muscles. These are the muscles that actually contract the lens so that it can focus correctly on the back of your eyeball. G is the vitreous body. It just makes sure that it's like inflating your eyeball, keeping it the right shape. Okay. H is not just this one spot. It is all of the yellow in the back, right? All of that whole part of the back of the eyeball, all of that. That is called the retina. That is called the retina. So all of that is the retina. All of that is the retina. And retina actually is where you have cells that can sense light. All along the retina, you have those cells. But particularly, there is one spot labeled I right there. It's called the fovea. It has the greatest concentration of cones, specific light receptors, which we'll talk about later on, for you to be able to sense light. In fact, that spot I, the fovea, that is where your lens is focusing the light, because that's where you're most sensitive. Unfortunately, though, you got to send those signals up to your brain. And so you have this K, optic nerve. But the K optic nerve goes right through the retina. So that means that you have J, a blind spot. A spot in your eyeball, in your retina, that doesn't have any receptors, that cannot sense light. And so what's going on, if you see the happy face and the heart, when you look at things, remember it's inverted. When I am focusing on the happy face, it's focused on the retina. When I move the paper toward me, it moves the heart until finally I get it to be in the blind spot. Now, what's interesting here is that your brain fills in the blind spot. It's doing it right now. Your brain is filling in your blind spot right now. What it does is it does those microsaccades. It jumps around, it picks up information, it fills in that blind spot, so you don't have just this dark spot right in the middle of things. You're filling in your blind spot. And so when you're actually sensing and then that heart goes away, you'll notice that it is going to fill in the color of everything around it. So for mine, it's an off-white. It's not a pure white paper, and so everything looked off-white. It went away. You are sensing a blind spot, but you don't perceive that blind spot. That is the power of your perceptions. Let's talk about depth cues. Have you ever heard people talk about having a depth of field or no sense of depth, that kind of thing? Well, normally they're talking about what's called depth cues. Monocular means one eye. Binocular means two eyes. So we'll talk about the monocular depth cues today. We'll talk about the binocular depth cues maybe next time. So each of these depth cues are monocular. They only require one eyeball to do it. The first one is called accommodation. Now, in psychology, accommodation is used in a lot of different ways, but particularly in the eyeball, we're going to talk about accommodation in the sense that your eye actually senses how much it's being squeezed. So let me go back here. Remember, F is those ciliary muscles, right? You see F, those ciliary muscles? They're squeezing the lens so that it can focus in the right spot. So your brain says, well, I can sense how much that is squeezing, and based off of how much of that's squeezing, I know roughly how far away the object is that I should be focusing on. Now, remember, you have ciliary muscles in each eye, so you only need one at a time, and your brain says, hey, if I'm focusing on this, then based off of how much I'm contracting that particular muscle, I know that it must be 5 feet away, or however many feet away. Okay? That is the only one of these that doesn't require context of some form. That is just your eyeball that is doing it by itself. The rest of these require a certain amount of context to understand how far away something is or is not. So for example, in the picture that you see a man on the ledge, but that is a sidewalk. Batman and Robin are a sidewalk chalk drawing, right? There's no actual hole or anything else. It's just a drawing. But you perceive depth, right? You can perceive the depth because you have monocular depth cues, right? You can do this with one eye. One of these is familiar size. Familiar size is that what we do is we compare whatever we're looking at with other things that we know the size of. So for example, I know how big a police car is supposed to be. And if it's looking that small and far away, then I know that it's pretty far away because I know the size of a police car. I also know the things around it, how big they are in relative to the familiar size of the object. So, for example, I can see the policeman standing right there next to the familiar size of the police car. That all makes sense, right? Because of the familiar size. Sometimes in movies, for example, they will use familiar size to help create a trick your eyeballs. So for example, in the movies like The Hobbit, they will create, what they'll do is they'll make barrels that are like actually 6 feet tall. But because you know that a barrel is normally 3 feet tall, anyone standing next to the barrel looks really, really short because you know of how big a barrel is supposed to be. And this person's a lot shorter than the barrel. Based off the familiar size of the barrel, I can tell how big the person is supposed to be. Interposition is very simple. Don't let interposition be more complicated than it needs to be. All it is that the thing that covers up the other thing is closer to you. So, for example, in that picture, you see that Batman is slightly covering up Robin. Well, you know that Batman should be closer to you because he is covering up. The interposition of Batman and Robin means that Batman is closer to you. If I have an object, right, and that object is covering up another object, this is my phone, right, I know that this pen is closer to me because in my point of view, it's covering up my phone. So I know based off the interposition of the pen and the phone that the pen is closer to me. Linear perspective. Linear perspective has to do with parallel lines. Now this is what people think about when they think about train tracks off in the distance. Two parallel lines appear to get closer together the farther away they are in the distance. So for example, if you follow the line on the sidewalk, here, these lines that I'm drawing in are actually parallel to each other. But the farther away you get, the closer they look to each other. Linear perspective says that parallel lines get closer to each other the farther away that they are. Now, if you were someone who wanted to make, let's say, a street seem longer than it normally is, well, people know that normally streets have parallel lines. So for example, at Disneyland, the street actually widens as it gets farther away. And what that does is it makes the perception is that the street is longer. So as you go into Disneyland, for example, you'll go down the main street. Well, that main street is not a parallel street. It's actually widened because your brain normally thinks that streets should be parallel, and then that these, based on the way that they can converge, makes it look longer, farther away. Motion parallax. Motion parallax requires motion, right? So fine, requires motion. But have you ever been driving in a car and you look outside and there's like a fence that's pretty close to the street, and then in the distance maybe there's some mountains or trees far away? The fence is going to look like it's going past you really quickly, but the mountains in the distance look like they're hardly moving at all. That's motion parallax. Things that are closer to you when you're moving look like they're moving farther than things that are farther away. So for example, as I move my head right now, my computer screen looks like it's moving quite a bit, but the wall way back there doesn't look like it's moving very much at all. Okay, the computer screen looks like it's moving a lot, and the wall doesn't look like it's moving very much. Things that are closer to you will move faster. So how do you use this? Well, the way you use this, if you're Disneyland, is you have a roller coaster like Space Mountain that has lights that pass you as you're going. And because the lights are moving that way, it makes you feel like you're going faster. Relative height. Relative height means that when we look at any image, something that is closer to the horizon should be higher up. Something that is closer to me should be lower down. It's the relative height of the images on the horizon. So for example, in this image that you see right here, this person, right, this person right here is higher up in the image than this person is. Based off of their relative height, I know that this person is farther away because it's higher up in the image, closer to the horizon. Shadow. Shadow just says that where the shadow falls, you can tell how far away the object is from its background, right? So if you see, there's actually some shadows there for Batman and Robin. They're kind of separated from their body, right? The more separated the shadow is from the object, the farther it is from the background. Texture gradient. You can see the texture of things that are closer to you. Things that are farther of you, you cannot distinguish texture. And so you shouldn't be able, so things that are farther away, they look more smooth, is what we're saying. In Cinderella's castle at Disneyland, again, another Disneyland thing, the highest part of the spire actually is painted so that it's smoother. Well, because of that smoothness, it makes it look farther away, because if it was closer, you'd expect to be able to understand and be able to see the texture. But because it's smooth, it makes it look farther away. You cannot see the individual stones, for example. They're smoothed out, making it appear farther away. These are all monocular depth cues. They require only one eye. So if anybody says that you have no depth perception if you only have one eye, that's not true. You don't have binocular depth perception, but you do have monocular depth perception. All right. Which of the following involves the shape of the lens? Accommodation. Accommodation involves the shape of the lens, right? You sense how much the ciliary muscles are contracting and changing the shape of the lens, and that means how far away the thing is going to be. Okay. I want you to look at these two people. So what is the upshot? The upshot is you can combine these monocular depth cues to create perceptual illusions. You see these two people? You see a man and a woman? The man is taller than the woman. You're like, what? The man is taller than the woman. I want you to watch this video. The video that you just watched was of an Ames room. An Ames room is a room where you have to look into one specific part, but nothing in the room is parallel. And they use these different cues that we've talked about to create a perceptual illusion. So for example, None of the tiles on the floor are actually parallel with each other. The roof itself slants. So does the floor. The familiar size of the clock is different. All of these things combine to create a perceptual illusion. Not that your eye is wrong, but your brain putting the information together gets confused, gets tricked. All right, we'll talk more about this in the second video. Thanks, everyone.